parameters covered. Okay. Now we are going a little bit quickly. Those of you who are familiar with this, there is not much of a problem. But those of you who are doing it for the first time, they will have a little bit of problem. Okay. So what I would suggest is that as we go along, we will keep revising also. Okay. So like Saturday, we have assignments on the transformations, forward kinematics, inverse kinematics, so which we can revise. So what's important here is to correlate the mathematics with the real world. So when a robot is moving in space, how the translation and the rotations are taking place, and how do you correlate that to the base frame? Because that is what is important, and you should understand that in terms of the physics of the system. Okay? So as we go along, things will get clearer. Okay? So in general, are you understanding? Or there is a problem? Say the rotation matrix, the homogeneous transformation matrix, okay, that you understood. Okay. DS parameter, there is a little problem. DS parameter, first time when you do, there is a problem. Okay. Yeah, so some confusion will come. So that again tomorrow morning we will revise again. So we'll keep doing whatever is not clear. We will because some things you must understand, you must know. Rotation matrix, transformation matrix, DS parameter, forward inverse kinematics, that you must know. Right? Okay, so as we go along, we'll be clarifying also. Now let's move on a little bit, because today in the afternoon we have the lab sessions also. So what we'll do is we'll cover a little bit of robot programming, which we are going to need in the lab session. So today in the lab, we'll be doing robot programming of an industrial robot, and then we'll look at sensor interface, microcontrollers, etc. So that is what we'll start in the afternoon today. So for that, what you need to know is the basic robot programming in VAL language. Okay, so a robot essentially interacts with. So a robot essentially interacts with other machines, right? A robot will not be working only on its own. So we will not just have a simple robot which will pick up something and will place something. Even if it has to pick up something and place something, what will happen is it will need some kind of. So which is better? This is better, or without the mic is better? Without mic. Okay, so well, I'll put the mic down so it will be. Okay, so essentially what we are seeing here is that a robot needs to interact with other machines also. So it has to communicate. For example, if a part has come on the part's arrival, then the part's carousel must be having some way of telling the robot that the part has come. Okay. Then it will start its program to try and pick it up. After it has picked it up, then again the robot should be able to tell the carousel that I have picked it up, so you can continue. Okay. Then the robot should be able to pick up something from here, put it on the work table, okay, and inform the work table or the machine table that the part has been put there. So some communication is required. Okay. Plus the robot has its own program, that is to do kinematics and control, etc. So here basically what we are trying to see is what is the program by which the robot interacts with the world, and how does it communicate. Okay. Now if the user of a robot has to study a course in robotics, at least a few courses in robotics, and then write inverse kinematics, forward kinematics, and then program the robot in assembly language, nobody likes robots. So the robot manufacturers have used a very simple language by which you can interact with the robot without knowing anything to do with transformations and rotations and all that. And it is essentially done so that you make it very easy for the person to interact. So essentially the robot programming language will be an easy language. Okay? And the person need not know anything about forward kinematics, inverse kinematics, rotation matrices. They need to know. Okay? That is taken care of at the lower level of the language. Okay? Plus the communication. So machines have to communicate with one another. Okay? They must have simple communication to tell this machine that a part has come, or the job has been finished, or So there also has to be some kind of sensor interface which is going on. Okay. So this assembly, this robot, this takes care of all of these parameters. Now, the general structure of a robot hardware, it consists of the mechanical hardware, the arms, motion transmission, gripper, etc., which is the mechanical part of the robot. Then there is the robot control unit, which consists of the robot controller itself. Okay. It could be PD controller, PID controller, or more advanced controllers. Then there are motors, which are actuators. Then there are sensors. Okay. Sensors for taking care of the internal working of the robot, plus interacting with the world. Motor drivers, power amplifiers, which are basic for driving the motors. You need current, so you have to use the amplifier. Then there is some kind of ADCs, analog to digital converters, digital to analog converters. This is essentially for interacting with sensors. So a lot of the data in the real world are analog, so it has to be converted to digital before the robot can read. So the robot also would be having ADCs, DSCs. It can also have other signal conditioning systems. So all of this comes as a part of the robot controller. Then there is a central controller for interfacing the robot with other machines. So the part of the central controller is essentially communication with other machines. Okay? So the robot general structure would consist of all these three units in one box. And as we go along, we'll be looking at this. We started looking at this, then we'll look at this, then we'll look at that. And towards the end, you'll be able to understand better what are the various systems involved. There are two ways of teaching a robot. The first way is by using a teach pendant. So the teach pendant is something like the remote of a TV or any kind of remote, say something like this. Okay? So there will be the joint numbers 1, 2, 3, 4, 5, 6, and there is plus, minus, plus, minus. So simply by taking the teach pendant and pressing plus or minus, you can take a particular joint and move it in space. So when it is moving in space, in the memory, the end effector position and orientation is also getting recorded. Okay? So you can physically, if I want to pick up this object, you can take the teach pendant. Suppose the robot arm is here, press the corresponding joints, take it till here, catch this object, pick it up, and put it there. Okay? So manually you can do that using teach pendant. And as the robot is moving in space, all these points are getting recorded in the memory. So if you want to play it back, then you can play it back. It will simply do the same motion over and over again. Okay? Now, why have this and also this? Now, this is the program-based control in which we have a program, okay, in which the control is essentially taken care of by the program itself. Now, a program, like other programs, will consist of lines, line numbers, some execution commands, some logic, and all that. So we have both ways of programming the robot. Now, this, why have two ways? Number one is, if I want to find the position orientation of a point in space, it is extremely difficult, if not impossible. The robot is fixed here. This is my robot. I want to go to this position and orientation. Okay, so the end effector should go like this with some orientation. Now, if I say what is the position and orientation of this point of the end effector, can you tell me with respect to this? No sensor will give you that. That means it needs 6 coordinates, 3 translations, 3 rotations. Now, no sensor will give you that. Okay? So if I want to pick up an object, it's very easy to say, go here, pick up the object. What is the position orientation? It's very difficult to find out. Okay? That is why you can actually find these positions out by using this one. So you can manually take it there, and then in the memory it is showing you what is the position orientation of this. Now you know what is the position orientation of this, and then you can program it. Okay? So the other thing is, this is very inefficient. Okay? Because is it optimal whether I'm taking the path like this or I'm taking like this? There are infinite solutions. Which path will I take? Right? So this is one way of finding out position orientations, but it is a very inefficient way of doing it. Okay? So the efficient way is this one, once you know the position orientation. But both are there, both ways by which we can program the robot. Now, like robotic systems, there are the languages of robots have also progressed, and there are 3 generations of languages. The first generation language essentially has simple commands for pick and place, and it has limited interaction with the world. For example, it has on-off switches and all that. Okay? So this is the first generation language, which is about 1960s. Okay? The 1960s, when the robots were first made, these languages were generated or developed for doing this simple application. Now, in the second generation languages, from about 1970s, 80s, what happened is there was more interaction with the environment. Okay? So when the interaction with the environment increased, then you needed more sensors, force sensors, touch sensors, ADCs, DSCs, vision, all that coming inside. Okay? So about 1990s, the second generation languages came up, and we are somewhere here now. So most of the robots are using second generation languages. They can interact with the world by means of different sensors. Third generation languages are what we call intelligent languages. Now they have a capacity to understand general commands. Okay? For example, if the worker in factory says that pick up this object and keep it there, that is English language. The robot doesn't understand. So the robot should be able to understand that and interpret it that this object has been picked up and kept there. Okay. Now, if a language can do that, then we can say that it's an intelligent language. But this hasn't got very far, essentially because language can be interpreted in different ways. And so it is very confusing for a machine to actually understand what is being said. Okay. So for example, if you say tighten a nut, whether it's a mechanical nut or it's a biological nut, you don't know what is the meaning of this. So different people can interpret it differently, or the context is context sensitive. Okay, what is it that you're saying? Okay. So a machine always gets confused. Now, why would you want this? Because most of the cost for a robot, 20% of the cost is actually the hardware cost. The 80% of the cost is the software cost, maintenance, programming, all that. Okay. So if you can make this programming part very easy by using a language which can be understood very easily, then it would bring down the cost. But not much progress has been made here in terms of learning of a language, or rather interpreting of a language. So this is where we are. People are struggling. Mainly in the CS community, they all, computer science people talk about intelligent languages. That is how to understand, how to interpret. Okay? So we are here. So the language we'll be learning is second language for interfacing with all these sensors of the robot. Now, as the languages have progressed, there are three different languages which were essentially started off in the early days. The first language is called VAL, which is Victor's assembly language, probably the name of the person Victor, who developed this language in 1960 with the Unimation robot called PUMA robot. So this is primary universal machine for assembly. So the first robot that was made in 1960 by this Unimation corporation, it was made for assembly in the automobile sector. Okay? So this robot was called PUMA, and the language that was used to program PUMA is essentially called the VAL language. So VAL language has VAL 1, VAL 2, VAL 3. The structure of this VAL language is basically based on the basic language. For those of you who have programmed something in basic language. So the basic language has a particular structure. There is a line number, then there is a command, then there is a line number command. So when you execute that language, it takes line by line and keeps going like that. Okay, so that is the basic language. So the VAL language has a structure of the basic language. And this was developed by Unimation Corporation. Unimation was an American company. It is gone now. It was bought over by Kawasaki. So now it is Kawasaki which is making the PUMA robot. So this is the robot we have in the lab, one of the robots we have. So we'll be learning programming of this. This is an industrial robot. It can be used for pick place, welding, all kinds of applications. And the fundamental difference between this and this is the background language of this is basic language. So the structure is very basic language. The second language is AML, which was developed by IBM. So IBM was also making robots about 1960s. But since then, IBM has closed their robotics. So this language is no more there. The third is RPL. So RPL was also about 1960s. So other companies were also making robots. This is a long time ago, 1960s, 70s. And this is based on the Fortran language. So the basic language is, here it is basic, here it was C-like, and here it is Fortran. So the background language and the structure of the language would be a little different. So this is also no more there. So 99.5% robots use VAL language or some derivative of VAL. So any robot that you will be looking at, industrial robot today, it will be using a variation of VAL language. So the commands will remain the same. A little structural difference here and there. So we'll be looking at VAL 2. So we had VAL 1 and then we had VAL 2. Now, what does this VAL language program consist of? What does the program look like? So we'll be looking at VAL 2 language, which can be used for the PUMA robot and most industrial robots of today. So the basic structure of the VAL 2 language is that when we write a program, the first thing would be the constants, variables, and data objects. So our program will be in this order when we write the program. So the first is going to be constants, variables, and data objects. Constants are constants. For example, if you're saying pi is 22 by 7, then that's a constant. Then variables. Now variables can be, for example, a point. A point in space here is a variable. You can assign different values to it. So you have to define your variables, you have to define your constants, and you can define your data objects. Now data objects is something like C. You can have a class and have an object. Okay? So you can define the constants, variables, and data objects. As we go along, we'll see how that is done. So this is the first. You define all your constants, variables. Number two is you define your motion control commands. A robot, unlike any other machine, moves around. So there has to be motion control commands. For example, very simple, move here, move there. Okay? motion control commands. Then the third is robot hand control command. So a robot also has a hand which open, close, or it will have a tool which will do something. So the third is robot hand control, which can be simple open, close, or it can be having a tool to do something. The fourth part is program control, input output control. So if there is some interface with some other machine or with a sensor input coming somewhere, okay, then this is the part that takes care of this sensor input, output, logical statements, etc. So structure of the program will be something like this. We'll start off with constants, variables, data objects, then have motion control commands, then robot hand control, and then program control and input output. So the program will be having a structure which is like this. Okay. So the first part is variables and motion control. In terms of variables, when a robot is moving in space, what is it that we are defining? We are defining it to go from one point to another point. Okay. So we have to define the points in space. So the first thing that we are doing is we are defining a point. This is the variable name P1. It can be 8 letters. It can be a combination of letters and numbers. Okay. So this is the name. It says that a point, P1 is a point, and these three are the coordinates in space with respect to the base 0, 0, 0, and this is the angle of the end effector. Okay. So if I say a point P1 is at this point, I have to say what is x, y, z of that point, plus I have to say what is the angles with respect to either the base with its own coordinate system. Okay. So here we are saying the point P1, so the variable name is P1, x, y, z is the coordinates of the point, and theta, alpha, and gamma are the orientation of the point. So 6 of them are required. If I am not interested in this, I can simply say x, y, z, and that it will take some default value. Okay. So the first thing we need to define is points in space, because the robot moves from point to point. Now once you have defined your points, the next thing would be the move command, the motion control. Move command is very easy. Move P1 and moves P1. There are two commands here. So one is move P1. It moves to the point P1. So it moves to the point P1, and here there is a command called move S. It also moves to the point P1, but it moves in a straight line. Okay. So it will move from here to here. This command is a motion control command, move and moves. This is P1. The point is the same point P1, but there are two different commands. Okay. Now why have two different commands? Now let's come here and try and understand that a little bit. Suppose we have three links, we have three joints of this manipulator system, and I'm at this point, and I want to go to that point. Suppose there is another point here I want to go. I define this as point P1, x, y, z, and the three angles. Okay. Now I want it to go from here to here. How will it go? What I mean is, will it take this path? Will it take this path? It will take this path. Which path will it take? It is at this point, it has to go to that point. I'm at this point, I want to go to this point. I can go like this, I can go like this, I can go like this. This three-dimensional space. I can go in infinite ways. Which one will I take? So here in robotics, this question always comes up because there are infinite ways by which you can go. If I give you just 2 points in space, then you can go from one point to another point in infinite ways. Which one will you take? Yeah, so we'll be requiring we will take a path which is going to minimize the energy requirement. Okay, there is no point in spending energy, right? So it is going to take the path which is going to take the minimum energy requirement. Okay. Now, if you have three joints like this, and you want to go from this point to this point, can you suggest a way of minimizing energy? This is a very important question in robotics. As we go along, everywhere this thing will come. That you are having to optimize energy in all your paths. How do you decide which is an energy optimal path now? Okay. There are three joints. Your actuators are here, here, and here. I want to go from here to there. There are three joints. Can you suggest a way by which it can go from here to here by using minimum energy? Let's come back to the question. I have an object here, okay, and I want to keep it, catch it from here and keep it here. So when you are catching an object like this and like this, your hand has 7 degrees of freedom. 3 to 2, that is 7. So it has infinite ways by which you can do. Which trajectory are you taking? we all do it in the same way. So which means that something is going on. So which trajectory are you taking? Are you taking a straight line? No, we never take straight line. Energy is work. Energy means work only. So which path am I going to take? So if I were to put this as a mathematical problem of optimization of three variables, theta 1, theta 2, theta 3, least of what? Yeah, so the way would be to take the least number of joints which are moving to take it from there to there, right? That is saying the same thing, that you move the joint, the least motion, so it is called the least angle norm. So the motion of this combination of these joint angles motion should be minimal. Okay. Now if you want to go from here to here, which one if you move it will simply take you from here to here. If I keep this fixed and I keep that fixed and I simply move this will simply go from here to here. So when I move like this, which is the joint which is moving? This one. This joint is not moving. The other joints are not moving. So this is called the least angle norm. So move the joints which will take the least number of joints such that you can go from another position to another position and do the task. That will take least energy. Okay. So first thing is least energy norm. Move the least, the smallest, least number of joints to take it from one point. Now if you do that, we see that if I move this joint only, it will go from here to here. Will that path be a straight line? No, it will not be a straight line. And hence if you see all our motions, they are not straight lines. Actually straight line takes a lot of more energy. Okay. So if you want to go from one point to another point, we move the least angles involved, and that normally is it's a curve in space. It will not be a straight line. Now, so that is what this command move will do. So if you go to move P1, it will take the least energy norm and go to P1. Now, there are applications where you have to move in a straight line. For example, when we are doing assembly. Now, these robots are used for assembling electronic components. Okay? Now, these electronic components, mobile phones, computers, laptops, TVs, everything is assembled by robots only. And assembled robots means they have to fix these chips in this motherboard. Now, if you look at the electronic chips, they are very small and they have these legs. So it essentially means that you have to move straight. You can't move at an angle. If you move at an angle, what will happen? The leg will break. So assembly robots always require one motion which is straight. Now for that, if you want a straight motion, then we can use this command which says move S. So move straight to the point P1. Okay. Now this takes more energy. Why does it take more energy? Because if you just think a little bit, if you are going from here to here in a straight line, what does it mean? It means that a straight line is a connection of infinite points. So it will have to compute every point on that line, and for every point it has to do the inverse kinematics and find the corresponding angle, and then it can go there. Okay. So it is going to take a lot of more energy. It will take a lot of more, because it has to do inverse kinematics for a very large number of points. Otherwise, it cannot go in a straight line. Okay. So if you want the robot to actually follow a straight line, then you have to use the command. Okay. For assembly, this is used just for moving in space. Again, for picking up an object, for example, when we pick up an object, we always go like this, and we catch it and we go like that. Okay. So this motion is always straight. Unlike a human normally goes from the side. A robot goes from the top. Okay. Because the chances of hitting something are much lower there. Draw is an incremental command, 45, 56, 60. Suppose I say move P1 and I want to make a small correction on P1. Then I can say draw. So this is an incremental command on this. It will make the correction on that quadrant. Suppose it has gone to some point. I want to incrementally correct it. Then I can simply say draw this. Next is approach P1 50. So approach command essentially is used for catching an object. So when we catch an object, we don't go straight to the object. We first go and stand on top. Okay. So this is saying approach the point P1. Suppose this is the point P1. So I'll say approach P1, so it will go on top and keep a distance of 50 along the z-axis. So it is not going straight to P1. It is going to approach P1 and keep a distance of 50 on top of P1. Then I can say moves P1, then comes down, okay, then catch it, and then go up. Okay. So this one, this is the coordinate of the point P1. X, Y, Z in terms of the base coordinate frame, 0 frame. This is the orientation of the end effector. So the robot has a hand, right? So the robot will have a hand, right, like this. So if I simply say XYZ here, the orientation could be anywhere. The XYZ is still same. So in my hand also, if this is my XYZ, then it could have a different orientation with the same XYZ. Right? So you have to define the position and orientation. So this is giving me the orientation. This is giving me the position of the end effector. Draw. Draw means after I've gone here, suppose I find that it was not exactly correct. I want to make small change here, here, or here. Then we can say that you draw from the last position 45, 56, 60, so that it makes a small correction on the previous command. This is an incremental command, this is an absolute command. This is absolute, this is incremental. No. This is XYZ is XYZ in the place of. You can also have another 3 here. 3 plus for it. Yes. So this is incremental. Incremental on the last command. Last was this one. It can change if you put orientation also. Yes. 6 or 7. Otherwise it will use this one only. Approach P1 is so approach is going on top and keeping a distance. Then we say moves, it go down. Catches, then we say depart. Depart is the opposite of approach. Depart is going backward. Okay, so this is approach, this is depart. So depart is it will go back after catching and keep a distance of 50 from the point P1. It is always along z axis. So the base coordinate frame is kept in such a way that this is x, y, and that is z of the robot, the 0 frame. So z is always in that direction. So all the approaches are always towards z. So there are only these 3 commands, actually just 2 commands. One is move, the other is moves. Okay. Approach, depart is logical command. So in terms of ease of programming, it's very easy. All you need to do is to use move and moves and approach and depart. You don't need to do anything else. Okay. So any program can be written simply by using these 4 commands only. Okay. Now this is the move motion control command. Next is the hand control command. One is open and close, and the other is open eye and close eye. Okay. So open close is, as the name indicates, open and close. Open means it will open the hand. Close means it will close the hand. Now let's look at this example here. So we have this example here that I want to go and catch this object, okay, which is kept on a table. This is my point P1. So the robot was somewhere else. So what I will do is I will bring it here like that. And so I will write a program, very simple one. So we say that the point P1, so first we say approach P1 and keep 150 distance. So it is standing there now. Okay. Then I say open. So line number 10, line number 20. So we say open. Okay. So it is opening. Then I say move. Moves P1. So moves, S is moving in a straight line. So it is moving down. Then I say close. Okay. So it's closing. Then I say depart. Depart P1 and go back there at 150. Okay. Then you can say move somewhere else and do something else. So this is just a very basic. I want to pick up this object. So it goes on top and stands there first using approach P1. This is my point P1. I have taught P1 equal to something. So P1 equal to, I have already taught all that, where it is. Okay. So all this I have taught, so it knows where is P1. I approach P1 and keep a distance of 150. So this distance is 150. Then I say open, open. Then I say moves P1, moves this way, it goes to P1. Then I say close, the hand closes. Then I say depart P1, 150, it goes back there. Okay, very simple. Okay. Now, you understand this, right? So normally the CG is given as P1. So that depends on the length of the finger and all that. But that is taken care of. I assume that my point P1 is appropriately chosen, either it is there or it is there. That is chosen properly. Which one? Depart P1, 150. Departs means straight, it means more or less the same. From here to here. So that is 150. Yeah, so wherever is P1, From here, it will take 150 there and stop there. Okay. There can be tools, there can be other things. In this case, I am saying there is a gripper. Okay. So, here, if I draw it correctly, so the first one is it is so when it is there, it is closed, and it is coming from closed position. Okay. So now we are saying that it is coming there, approach P1, it has gone there, then we say open, then we say moves P1, and then we say close, and then we say depart. Yeah, so this has been taken care of. Whoever is writing the program has measured all those distances and put the correct distance. Okay. So those things are correct. Now, in terms of logic, is this okay? Or there is a problem? In terms of logic. So would this be okay, or there is a chance of an accident here? So it is here, it is going there. Then we are saying open, then it moves down there, then it closes, goes back, and goes somewhere else. Home and all is coming there, so robot is already is home, then everything is okay. It was doing something else at some other time, then it's come. So there is something in the program here, there will be something in the program there. I'm just looking at this part of the program, so that it has to catch this. Is it correct, or there is a chance of a problem here? Gravity is this side, that's okay. Open first, okay, you want to put open here. Okay, open first and then approach. No, this will, even if this will not hit, because the reason for giving this is always it comes in the Z direction and it comes on top. That is the way it is given like that. So the robot could have been here doing something else under the table maybe. Okay. So the robot could have been doing something here. So the moment it gets this one, it means that it has to come on the top. So it will come like this from the top and then wait. It is all taught in P1. So P1 we have already taught everything. What is the problem here? Now the problem here is the way a program executes, the way any program executes, is you have a compiler. Okay? The compiler will execute line by line. That's how a program executes. Okay? So we have a compiler and we have a hardware, which is the robot. So the compiler will start processing this language, this line. So we'll say approach P1 150. So it will come there. Okay? So as far as the compiler is considered, this is done. Then next it will go to the next line and say open. Now as far as the compiler is considered, open means open. So it will give the command to the actual robot hardware to open. Okay? Now the moment it gives that command, as far as the compiler is considered, it has already executed this command. So it comes to the next line. It says moves P1. You follow? So what is happening is when it is saying open, it is opening slowly. It will take time to open. But when it has given the command open, this line is executed, it goes to the next line. So when this fellow is opening, it is also moving. Right? Because as far as the compiler is considered, it doesn't care about the hardware on this side. Right? So it is just a compiler which is compiling this and giving it to the hardware on the other side. So it will, when it is opening, it is going to start moving. And what can happen, if it is not fully open, it will come and hit this one. The same thing happens here. So it has come down like this. Now we say close. As far as the compiler is considered, it is closing. And this line is executed, so it goes to the next line. So when it is closing, it has not fully closed, it has started moving also. So there is this problem that can happen if you have not taken care of that. That this is a real hardware which is interfacing with a software compiler now. Okay? So there has to be some way to avoid this, and to avoid this, we need a closed loop command which is called open I or close I. Okay? So we have open and close. And we have another set of commands called open I and close I. Now open I and close I means open immediate and close immediate. This is a feedback closed loop command. So when it will open I, it will open, and unless it is fully open, it will not go to the next line. It will wait for the signal that it is fully open. Only then the compiler will go to the next line. So if I write open I there, then after this line is fully executed, then it will go to the next line. Otherwise it won't go. Then the question comes, why have two commands? So most of them are pneumatic type only. Most grippers in the industry also are pneumatic. So then why have two commands? Yes, because this is an open loop command, this is a closed loop command. Now because this being closed loop, it will take more time. Okay. Right. So if you want to make your cycle time more efficient, more and more efficient, then you have to use commands which are the least time taking commands and not closed loop commands. Okay. So this one will take you, give you an open closed loop command. So if the robot is somewhere else doing something else, so you can, when it is moving from there to here, you can open it. And if you are sure that it has opened by the time it has come here, then you can simply go ahead with this command only. It will take less time. Okay. Or if a robot is moving in space, not doing anything, then you can simply open it. Okay. So when it is moving, it's also opening. It's okay. But in this kind of a case, we have to be careful whether you're using this one or this one, because the cycle time is different. Now, a robot will not do one task for only one time. Okay. So we can argue that this will take maybe, say, at the fastest will be what, 0.5 seconds or 0.1 second maybe. Okay, very fast robot will figure it in 0.1 second. Okay. Now, even if it is 0.1 second, and if it is doing millions of cycles, then 0.1 second into millions of cycles is a very large time. So as far as the robot is considered, even a fraction of a second, okay, is valuable. And that is what makes the programming very difficult. How to optimize cycle time now. Okay. So, so when we are writing the program, we have to be careful of these small things, that we have to be careful that it doesn't hit and there is a logical flaw somewhere. Okay. So this one seems okay, but it's not okay. Okay. So these are things that we need to be very, very careful of. The second is command is speed. You can set the speed as 60 IPS is inches per second, or you can set it as meters per second. Now, another interesting point, another interesting thing here is, suppose we are going to pick up an object from here and keep it here, 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 like that. So this is a palleting table or indexing table. So we are going to pick up one part which is coming from a conveyor. So when the part comes there, it informs the robot that the part has come, and the conveyor stops. Then the robot goes and picks up the part. The robot then informs the conveyor that I have picked it up, so it will start again. Okay. Then it will take the part, put it here. Okay. Then it will take the next one, put it here. Then here, 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 here. Right? This is indexing. Now, again the question comes up whether it will go here, 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 then here, 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 like this, or it will go here, 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 then go here, 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 then here, 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 or it will go like this. Which will give you the less time, least time? Because a fraction of a second is also very, very important here now. We are talking of millions of cycles. The robot will work three shifts, 24 hours a day for years. So even a small delay somewhere will cause a big change at the end of the day. Which will give you the fastest way of doing the task? I hope the question is clear. You have to pick up from here, put here, 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 and then like this, or you go like this, or you go like this, like this. So many ways. Which way? Yes, but which one takes least time? So which one will take the least time? So you're saying like this. Like this. But the answer will surprise you. All will take the same time. Why? Because it's a sigma of time from here, here, here. So if you do sigma of time, it is addition. So it's commutative. So if you change that time, it is the sigma of all the times. And addition is commutative, isn't it? So it has to go to all the points. So in which order it goes to all the points doesn't matter. It has to fill up all of them. No, then also this question would come if there is only 4. Does it do like this, like this, like this, like this, or it does like this, or like this, like this? The question is still there. right? It has to go to every point in space. So at the end of the day, it is the sum of all the times, and addition is commutative. Oh, well, if saying only 4, don't go till here, go here. Yeah, okay, yeah. Okay. But in general, in indexing, you normally can go like this, like this, like this, like this. So what is done is like this, like this, like this. So this is where there is a question again of time, and which is the fastest way. There is something called deadlock, which we have to be careful of here. What is deadlock is that essentially the robot picks up a part, puts it here, okay. Then the part is machined here, it takes it up, puts it here, then from here it takes it there, and then puts it somewhere else. Now suppose the robot has picked up a part and put it here. The machining is going on. Now a second part has come, the robot has picked up this part again. Now after the machining is over, the robot has no space to take it and put it there now. So what has happened, it has got deadlock now. Okay. So the robot can pick up a part only if its gripper is free, not otherwise. So suppose it has picked up a part and put it there, and next after the machining is over, the robot has to pick this up and put it there. But in the meantime, it has picked up another one. Now it has nowhere to keep this one, and the part is already here. Okay, so you are locked now. Okay. So the program has got locked, which is called deadlock. Now, how do robots communicate, or how do machines communicate? So they essentially communicate by means at the simplest level. Okay. The machines communicate by using high and low signals at the lowest level. What is this high and low signal? So the robot would be connected to, let's talk about this one. So there would be channels of the robot. Channels would mean simple wires, we can say. Okay. So here there will be particular channels. So channel number 1 of this is connected to channel number 1 of that. Okay. And the robot or the conveyor will simply, when the part comes, it will simply make it high. High means it will make it 5 volts. Okay. Now the robot understands that if channel 1 is high, means the part has come now. Okay. So at the lowest level, we can communicate between machines by using high and low signals through particular channels. That's the lowest level of communication. So the syntax for doing this is essentially, it is called signal. Okay. Signal stands for signal, and this is the channel number, 2, 3. Okay. So robot will be having many channels. Okay. And this means channel number 2 is plus and channel number 3 is minus. So we can use different kind of logical statements. For example, go to 20. This is a basic language structure. So go to 20 means go to line number 20. Then go sub is go to a subroutine. After the subroutine is executed, return. Then if then else statement. Okay. Then pause, proceed. So we can use a statement like this. If signal is 2 and minus 3, then do something else, wait. Okay. So this means if signals on channel number 2 is plus and channel number 3 is minus, then you execute, say, pickup object. Else, you wait. Okay. So this is a logical statement which is telling the robot that wait for that signal first. If the part has come and you get this signal, then only do something. Else you can be doing something else. Okay. So if then else is one way of using signal. So wait signal minus 1, 2 says wait until signal minus 1 becomes minus and 2 becomes plus. So at the lowest level, the robot can communicate with other machines by using the SIG command. This stands for signal channel number plus minus. Okay. So logically we can configure it such that the robot's particular channels from here will go there, channel from here will come here, channel from there will come here. And by making them high, low, the robot can actually understand which machine is saying what. Now, this is essentially for very simple high-low kind of signals. Now, if the robot is interfacing with other kind of sensors, for example, force torque sensors, then cameras, okay, then some of the sensors could be giving you analog feedback. So for example, you are measuring force using a strain gauge. In that case, your signal is an analog signal. An analog signal means a continuous time signal. Now, the robot cannot understand analog signal, so it has to convert it to an analog to digital converter, convert it to a digital signal, and then it can make some sense out of it. Okay. So the robot control hardware also has data acquisition hardware or signal processing hardware. So we can also give an input to an ADC from an analog sensor. It is going to convert it to digital, and now it can make sense out of it. Now it can be the other way around, that the robot may also need to communicate with other machines, in which case it has to give out a digital signal. Okay, so we have a DSC also. Then there can be counters, how many times it has executed a particular cycle. So there are counters which keeps time, which keeps count. then there are analog sensors which you can take in. So most of the robots can, nowadays, almost all the robots can take care of analog signals, digital signals, counters, sensors, can all take all kinds of signals. Okay. And there would be some kind of data acquisition hardware, signal processing hardware before the decision is taken in the program. So analog signals are essentially time varying signals, and they are converted to digital signals using ADCs. And how it is basically done is analog signals are sampled at particular frequencies, then converted into digital. Okay. So analog to digital conversion is there. Now you can also have a digital signal. Okay. For example, an encoder gives you a digital input. Okay. So you can have a continuously digital signal which is already digital. Okay. Or the robot may need to interface with some other machine, okay, in which requires the digital signal from the robot. So it has DSCs which can give out digital signals. So it both has ADCs and DSCs in particular channel numbers. One is analog to digital converter. This is a digital to analog converter. So robot can use this or this as. Now what is the syntax? The syntax is ADC1 is equal to sensor 1. So ADC1 name indicates ADC1. This is a channel number. So suppose I fix a sensor, force sensor onto a channel number 1. Then I can say X is equal, my value of force is equal to ADC1, and ADC1 is equal to sensor 1. Okay. So the commands are very simple and English-like. So move, open, close, signal, ADC, DSC. Okay. All you need to know is what is the action you want to take. So a sensor, if you are connecting a sensor here, we can simply connect it to channel number 1. So it's an analog signal, so it will be converted to digital, and then it will go on to the channel number 1. Then I can take some action. For example, if I'm inserting, so suppose the example is a cap and I'm assembling it onto here. So I also have a force torque sensor on my wrist. So when it is assembling, suppose the force is exceeding some value, then it should immediately stop or try and reverse. Okay. So what we can do is I can attach my force sensor onto my sensor 1 is a force sensor. Okay. So the ADC1 is taking the input as force which is coming from that sensor. So a logical statement can be if ADC1 is greater than the 10 newtons, then stop. Okay. So the statement can be very, very easily made by using the statements like either signal or by using ADC or by using DSC. Okay. So this is how other kind of sensors can interact with a robot. Yeah, IO put and IO get is to put a value onto that channel. Like in C language, I put something. So suppose you want to give 5 volt output onto some channel. Then you put an IO put 5 volts onto channel number 2. Okay. So wherever the channel number 2 is connected to whichever machine, it suddenly becomes high. Okay. So I put and I get is also another way of communicating. So this is almost similar to the signal command. This we are just giving input and output with a channel number for communication. ADC1 refers to the channel number 1. So ADC1 would be the ADC on the channel number 1. So ADCs will be having about 6 ADCs, ADC1, 2, 3, 4, 5, 6. So DSCs will be another 6, DSC1, 2, 3, 4, 5, 6. Okay. So that is the. Yes. So if I say X is equal to ADC1, then X is the whatever is coming in ADC1 is assigned the value X. Then I can say if X is greater than 10 newtons, then stop. Okay. So that is how it communicates with analog and digital signals. Now the robot can actually interface with a lot of other devices, not only with conveyors. It can go with AGVs, it can go with welding devices, and it can go with all kinds of other communication devices which are there. Now, another way of teaching a robot is by using this lead-through teaching. So a lot of the applications in the industry, a lot of them do not require contact. For example, spray painting does not require contact. You just have to move it in space. Spot welding, again, is at particular location. Okay. So spot welding, the positions are defined again. But certain things like, for example, welding. Okay. So in welding, there requires very, very precise and fine motion, which are very difficult to define mathematically. So the way welding is done is you take the electrode, touch it, come up, and the arc is generated, and then you have to have some kind of weaving pattern. Okay. and then as you're weaving, the electrode also has to be moved down. So to mathematically put an equation to that is difficult. So in that case, what is done is this lead through teaching is done, where there is an expert welder who is using something like a joystick and is performing exactly the same motions, and the motions are getting recorded here. And then on the other side, this is transmitted to the robot, and the robot is doing that. Okay. So this is called through teaching. So there are three ways. One is speech pendant. Number two is program. Number three is lead through teaching, where the human can actually take the robot and using a joystick and teach it to do something. Okay. Speech pendant is simply for moving the joints in space or doing something. This is teaching a complex task like welding or assembly, okay, where it is very difficult to mathematically define. Yeah. So for example, in assembly also, when you're assembling, it's very difficult actually to figure out, to mathematically write those equations. Okay. So it's interesting here that if you go to any robotics company anywhere in the world, okay, any robotics company anywhere, even the best companies in the world, in Japan or wherever, you'll always find some human beings hanging around somewhere. Okay. Even the best companies, okay, Fanuc and Hitachi and Toyota, you'll always find some human beings are doing something and they're always there. Okay. Although it's almost 100% automated. No, those are programmed already. Assembly line is programmed already. Okay. But there are some human beings who are doing something. Okay. So the question comes that do the companies want to keep these human beings, or that is why they are there, or is there some other reason, or is it because the robots cannot do particular tasks? So there's supposed to be a joke that in future, 200 years from now, there will be only two kinds of creatures. Companies will be fully automated. There will be only two kinds of persons, one human and one dog. And everything else is 100% automated. So what is the function of the human and the dog? So the function of the human is to feed the dog. And the function of the dog is to ensure the human does not touch anything. But we haven't got that far. So in robotics today, about 80 to 85% jobs can be automated. 15% still cannot be automated. So when we are applying a robot as we go along, we'll see that there are tasks which still cannot be automated, and because of which you'll always find these humans hanging around. Okay. And it's very interesting. Even very simple tasks, like putting a nut on a bolt, a robot cannot do. So when you go to the car companies, you'll see the person take a tire, he puts it in, then he takes a nut, he puts the nut, then he takes a power wrench, then he tightens the nut. No robot can do that. It is not that the companies don't want the robots to do it. In fact, if you look at the grand challenges of companies like Toyota and General Motors and Ford, they have a list of things which they want to automate. A very simple thing like this is one of their grand challenges. Yeah, the question is why? Because the motion of putting a nut cannot be defined mathematically. The moment you cannot define those positions in space, you cannot program a robot. A robot only understands those positions in space. So when you say I'm going to tighten a nut, how do you tighten a nut? How do you tighten a nut? How do you say you have a bolt and a nut? Yes, because it's a screw coordinate, yes. But my question is, if you go to these car companies, you see they do it very fast. They take a tire, they put the tire in the car, then they take a nut, again they do it very quickly. Then they use a power wrench. So the question is that, no, the question is, how does that fellow align the nut? No, all that is fine. You're not answering the question. No. The question is, when you have two threads, you want to match two threads now. How do you do it? Try and rotate clockwise, it will jump. You have to rotate anti-clockwise. If you see very carefully what this fellow is doing, he will not insert the nut and turn like this, he will turn on the other side. The moment you do anti-clockwise, then the two threads will fall into place. Then clockwise. Now that's English language, right? Human being understands that. Robot will not understand that. Because for a robot, it needs a trajectory, it needs positions in space. That is not defined. Because the starting point of your thread is going to change with every thread. You have a nut and a bolt with any angle. We feel. So the moment you're feeling when they fall in place, you get a small sound or you feel that, okay, it has set now. That a robot cannot do. Tightness, they use a power wrench. So companies, if there is a human being who is working for 3 shifts, okay, so he works for 8 hours. He takes a wheel, puts it, then puts the nut, takes a power wrench, tightens it. So for 8 hours a day, he is doing it for years. So what will happen after about 10 years is he will lose his joints, they will be damaged. Okay. So the company has to pay a lot of money. So at least over, that is English language again. So in overseas companies, they have to pay a lot of money for this kind of damages. Yeah, if you can do it, then you will get a lot of money. You can start a company which will actually automate. I'm serious. Serious. There are a lot of tasks which cannot be automated. One task is, I just gave an example. There are many examples like this. You go to the car companies, you will see human beings doing all this. In the best companies in the world. Why? Because those tasks cannot be automated. Okay? So when you're applying a robot, you should be careful that you don't try to make the robot do those tasks. It will not be possible. Another very interesting thing is if you go to any car company, even in India, in the door of the car, on the body, when you open the door, on the body there is a rubber padding. So how is that fitted? So there is a human being who will take that rubber, then he'll put it in his hand like this, then all around the door he'll do like this, like this, like this, and he'll fit the wire. Right? Anywhere in the world it's done like that. Why can't a robot do that? Because it is flexible. The points will change in space. The moment you catch it, that point will change. So the robot can't do anything about it. So it's serious stuff. Okay? Anything which is flexible, a robot cannot catch. It cannot catch cloth, it cannot catch rubber, it can't. Because those points are not fixed in space. In our program, you have to define P1. Now if P1 changes, the robot is finished. Right? So again, if a person is doing like this for 8 hours a day for 10 years, his hand will be gone. And this is a real problem. So overseas, they have to pay a lot of insurance and a lot of money to these people who are having this kind of injuries. And this is going to happen. So there are a lot of companies which pay a lot of money to, if you can invent some device which will solve these problems. So towards the end, when we come to industrial robotics, then we'll see what are these problems. 15% of jobs as of today cannot be automated because of these problems. Okay, let's stop.